Alright, welcome back to another video by Firestarter Graphics and Engineering. Today we're going to talk a little bit more about airfoil design and analysis. So, right before I start FEA analysis, I like to do what we call a basic static beam analysis, a force analysis. I kind of want a general idea of what's going to happen with my blade and the material. So, what are my first steps? Well, that's a great question. So I take this picture of my airfoil and I look at it and say, man, I wish I had an equation for this top curve and this bottom curve. Well, luckily there's a way in numerical methods to find that out. There's actually a few ways. There's the trapezoidal rule, there's the Simpson's 1/3 rule, there's Newton's rule, but today we're going to use Lagrange interpolation. And so, what that does is it takes your points, 1, 2, and 3. Okay, so that takes your points, like I said, 1, 2, and 3, and it's going to generate a curve. Because what it's doing is saying, hey, I'm going to take point 1, do some fancy algebraic math, and I'm going to make all these other points. I'm going to make the curve cross through here, but 0 everywhere else. And then on this one, I'm going to cross through here, but 0 through everywhere else. Same with point 3. And then we add them all together. That is the basic of Lagrange interpolation. If you want to know more, go ahead and YouTube it. There's actually some great videos that show how to do it and the theory behind it. Okay, so what would be the purpose of that? Well, the purpose of that is I would like to get the inner area of this surface right here. Because if I can find that, then I can use it for my force analysis by finding the second moment of inertia, using it as the area of the cross-sectional area. Okay, so this is how we do that. Let's go here. Okay, so I have all my dots plotted right here. This is actually from an A18 original airfoil. I downloaded the data, and I only plotted the first upper surface, the first camber line here. Now, you can do all this by hand, and it gets tedious after about an hour. Or you can come into Excel and write a formula that plots the points. Well, first you plot the points, but then you can write a formula that actually creates this line using the Lagrange interpolation method. However, there's even a quicker method. Once you have your data, you can just right-click in the chart and say Add Trend Line. And you're going to click it. And it's going to bring it up. And you're going to put in polynomial. And it's going to start out as a second order. So a quadratic, a parabolic. Which looks pretty good. I mean, for rough shape and a quick analysis, this would be good. But we can do better. So we're going to hit third order. We can see we do a little better, especially here. But right here we can even do better. We're going to do fourth order, and that's pretty good. Now if we do a fifth order, that gives us a sharper trailing edge, which I don't want for this particular case because my wind turbine blade does not have a sharp edge. It's rounded. So I'm going to go ahead and drop it back off to 4. Okay, so now we have my trend line. You can display the equation on the chart and your R-squared value. R-squared value is kind of like your error. It's how far away are you from the true line, the true value. And we're only 0.8%. We're very close to the original line. So the closer you are to 1, the better. And we're 99.12% there. That's what we want. Okay. Excuse me. Now what do we do? That's an excellent question. What you're going to want to do next is open up Desmos Graphing Calculator. And you're going to input the actual equation right here. Don't worry about the R-squared value, just input this, and it's going to go ahead and it's going to graph this red line. Okay, now we want to add a little bit of thickness to this. So for my case, I wanted 90%. So let me show you, and I wanted it translated. Let's get rid of the 0.9 first. Okay. So this is what I had. How did I shift it down? We wanted a vertical translation. All I did, if you remember from your good old math days, to do a translation with a polynomial, you just put a negative constant at the end or a positive constant to move it up or down. So put a -2, that just shifted it down. Now, if I want to control the height of this point for its thickness, I can do that. But if I want uniform thickness all the way, I just leave it like this. But let's add a little bit of, since we're experimenting, let's just kind of goof off a little bit. 0.1. Okay. That doesn't do much for us. I mean, it's kind of a cool shape. Okay, 0.2. And you can see it's just getting higher and higher. I mean, that's actually kind of a cool airfoil. And so if we put 9, it's close to not having that value at all, because it's really close to 1, obviously. So if we just keep putting 9s in there, you can see how it shifts it up to its original. But we just want 90%. So it kind of thins out right here and thickens, just for this example. But to make it simple, we are going to leave it as this. Okay, so now what do we do with this? Well, if you remember from calculus, you can find the area under the curve, or in the curve, or however you want to understand that, by integrating. So if I take this first function and integrate with my bounds from in x from 0 to roughly 72, and then I integrate the second function from 0 to 62.2, we'll get 2 values. Now if we find the difference between those values, that will be the area inside of here. And that is the area that we want. Now, we need to talk about something called the second moment of inertia. I'm not going to explain the physics behind it, but the calculation is needed. So, you're going to go over to Google or Bing or whatever search engine you use, and you're going to find a moment of inertia calculator. I prefer Omni Calculator. Now, you're going to use whatever shape, but we're going to stick with rectangular. You could do ellipse. You could probably get away with ellipse, but you'd have to have 2 of them to create that shape. Let's go back. So this is the first elliptical and the second elliptical shape. Gets a little complicated doing that, but we're going to stick with rectangular, and this is why. If we were to smash these, we can find the arc length from 0 to 71. We can find the length of this line. If we were to flatten it down, we would know its length. Or if we do other math, we can find its length. We can also find the length of this green line. It's not too bad to find. And that gives us, if we were to smash down, a rectangular shape. So, knowing that, if we know that this is going to be a certain height, and we know our total area, let's say our total area is 700 millimeters. We can say 700 is equal to base times height. If we at least know the height, we can solve for base. Kind of a basic principle like that. And then you're going to put it in here, and you're going to get this IX value back. Okay, so with that information, let's head over to another website I use, clearcalcs.com, for beam analysis, metric units. I went ahead and filled out everything already for the video. This is how long my blade length is. This is my Young's modulus from the last video you watched, where I actually did the tensile test on it. The tensile test on the material, and we actually got our real raw data back. This is the area of cross-section that I calculated with integration. And then using that information, a base and a height, for me, rectangularly, I put it in here, and I get this number back. Okay, so set yours to fixed. Originally, it'll be pinned. You don't need it pinned. You want it fixed at this one side. Then you're going to do distributed load, starting at 200 newtons. So 0.2, and it's going to end at 200 newtons. We want 200 newtons across the whole thing, so that it's this load. You don't want a distributed load like that. I don't know. It's easier just to do. You can mess with the loading here in a minute, but let's pretend that the wind is constant and we have a constant 200 newtons pushing on that blade. So, uniform. Now, if we go up here, you'll notice it's negative 124 millimeters of deflection. Comparing that to my FEA analysis of 127 in the negative direction. So we're really close. So this gives me a rough idea of what my deflection is going to be when I start working with an object. Now, the complexity of the geometry can be really tough to find the area of cross-section. So what I had to do, let's see, do I have a picture? Yeah, okay. We know right here it's pretty uniform. If we go right about here, it's pretty uniform shape. So I just took the area of each one of these airfoils, added them together, and found the average. And then I did the same thing. I mean, I could have found all of the averages, added them all together and found the average. But most of the material is right in here. So it's trying to find out, okay, if I were to draw a line straight across right here, I lose some, but I also gain some, but I lose some. So it's trying to find that perfect spot of where you can have a rectangular beam. So if I cut right here, I lose all of that beneath, but I also lose all of this empty space. So I'm hoping that this is enough to compensate for this. So that's why I was able to find the average. I just went with a thicker material, found the average of that, and all the averages of the airfoils, which hopefully yielded a decent average, which it must have, because it was only 3 millimeters difference. That's probably luck. So I would say rough guesstimate, you could be 30 points off in either direction, but at least it gives you a basic idea of what it's going to be. Now, if you're dealing with complex geometry that's not a single beam, like, I don't know, a chair, a desk, some sort of circular object, this would be pretty tough to use. But for wind turbine blades and a bolt and anything that you could probably somehow get a rectangular profile out of, this works great to give you a basic rundown and a basic analysis of what you have. And it also gives you your shear and your moment and your deflection. Gives you enough data to work with something. So, anyways, excuse me. Starting to, getting a little choked up. I love engineering. It's gonna make me cry. No, I just have something. I ate something spicy earlier, and one of those little pepper seeds, gets right there on the side of your mouth, and just, yes, sir. Anyways, thank you for watching. I hope you enjoyed it, and I know engineering topics are not always the funnest to discuss, and it can be pretty dry. But if you're in the field and you need information, and sometimes it's hard to come by, hopefully this will help you further. Hopefully this somehow helps you either with your schooling or a job. Anyways, thanks for watching, and talk to you next time.